point I talked about whited link, but I wrote figure of 8 knot. So evidently I meant whited link and not figure of 8 knot. Figure of 8 knot is something like this. I just so is over under over under, etc. The fact that a knot or a link goes over and under on strands means they are called alternating knots and links that gave hopes to Tate to classify all knots and links, and then he discovered that above a certain complexity, this over-under breaks down, and so it was a source of depression. Anyway, okay, so I've been asked to provide a little information on the thing. So we remember I just use two colors, let's see, to denote a link. It can be two-component link, something like this. We put orientation, and then for this object, this is a link. Then we introduce the linking number, and the linking number between say C1 and the curve C2 is just LK1, 2 of these two curves, C1 and C2. If we make these two curves to be vortex filament, then I used sometimes the letter L just to denote that there is vorticity there. And we said that this is given in general by this formula, R denoting the sites of crossing strands, and so epsilon R takes values plus minus 1, and we use this formula. So, well, this formula is related to, I'll be very, very brief, just to give you an idea. This formula is related to solid angle interpretation. I told you that linking number has many different, apparently different definitions, and proof of the topological invariance of linking number can be done through these several definitions. There are at least 8, 5 of which are mentioned in a paper that I produced, and I give you just a little reference. So we talked about the formula, the analytical formula, double integral of that quantity. Then I quickly showed you that this formula can be explicited in terms of solid angle. At a certain point I wrote something like this: R hat ds and divided by 4 pi r squared, if you like. And this is just the definition of the solid angle. And through this, you can get this information, i.e. the interpretation of linking numbers in terms of algebraic sum of crossing sites. And just to give you a very quick idea of how this can be, how this expression can be related to this, etc., I like to just give you an intuitive idea of what I mean. Imagine that these are two strands, very locally, of these two curves, and I take, say, 2 points, one here, one there. Let me call this point x, well, this curve described by the point by these points x1, and this curve given by x2, vector position of these points. And then these would be r, the difference between the point at x2 and the point at x1 of these two curves. And then imagine that from some direction you see an apparent crossing. Okay, so evidently there are no crossings on this plane on purpose, but imagine that you look these strands from some particular, some particular direction, and then you have something like this. I try not to mess up too much this. Imagine that this is some kind of confined region through which you see these two strands, and from a particular region, from a particular direction, say P, you see a crossing coming out. So when you so this would give you an elementary contribution to the solid angle, and when you integrate over all possible space directions in R3, then you get this. Each apparent crossing contribute to 1 or minus 1. So this is just a quick entry to that, too quick to really understand things. If you want to check on a paper, you will get the references anyway. But this is a paper that I wrote a few years back, and is in Journal of Knot Theory and ramification, and the paper concerns in the explicit derivations of 8 out of 11 different demonstrations of the linking number. All right, in an accessible way. Other techniques are just mentioned very quickly in a Spivak book. You know, it's a 5-volume book, and is a pretty hard on differential geometry and pretty hard to follow anyway. Okay, this is the case of a link. Now, what about a knot? We introduced knots yesterday, and the idea is the following. Okay, you have your preferred knot, say the trefoil knot, to keep things simple. And then I said, well, it's better to relate this to a ribbon. So you construct a second curve. Imagine that this second curve is very, very close to the first one. I emphasize this so that it looks like a tubular neighborhood, if you think of a center line there, or the two curves. Then you define a ribbon. Let me first quote the word knot. And then we have to look for something like this, and indeed it was found by Calogariano. I'm going to write it in a moment. The ribbon R is constructed on the basis of a central line. Let me take a C or L if it is a vortex line, and then a unit vector, a unit normal vector on this center line. This is one way to write it, and probably yesterday, the other day, I used an alternative way to write it is to use a C1 and a C2, and remember these two curves are related by an epsilon, and when you take the limit as epsilon goes to 0, then you get proof that this quantity self-linking number is a topological quantity. I'd like to quote this result. There's a result of a lot of work by, in particular, Calogariano. For a number of reasons, now this result is referred to Calogariano white. So I'm perfectly okay to quote both. So this is Calogariano white, and it says that the self-linking number, of let's say SL of R is a topological invariant. Be careful, don't say that is an invariant of the knot, because the knot is a curve in space. So you have to think of a thickened knot, so a ribbon. Okay, so it's a topological invariant of R, of this ribbon, and admits decomposition, admits decomposition. SL of R given by what is called the writhe of a center line, say C, plus the twist of this ribbon. Now I'm going to tell you something about these quantities where WR of C is the writhing number of C, and the twist, and TW of R is the total twist number. I'm almost done with all this introductory information on these quantities, but I actually needed, in order to talk about vortex aspects of vortex dynamics that involve topology, if you like. Okay, so what is the writhe and what is the twist? Now, the writhe of a curve is a geometric. Both these quantities are global geometric quantities, in particular of a curve and of a ribbon. And this is topological. So it's quite amazing to see that this quantity is almost identical to the linking number definition, except that is a double line integral on the same curve. The difference is that the linking number is a double integral on two different curves, C1 and C2, where here you have this information on a single line. And well, I reproduce the formula, but it's identical to the linking number formula. So we have an x and x star, and here x and x star are 2 points. Well, we can call it x1 and x2 if you like. I leave it like this, doesn't matter. And this is the wedge product of dx1, dx, and dx star. And as usual, we have x minus x star to the cube here. So if we have interpretation in terms of crossing sign of this quantity, the linking number, we expect to be able, because again we can read out the solid angle interpretation there, we expect to have the same type of interpretation for the writhe, so that instead of computing the writhe through this double integration on the same line, we can take advantage of the crossing sign expression, except that now, remember, this quantity is a geometric quantity, so we have to average out with these angle brackets, we have to average out this count on all possible directions. So you have your center line of your knot, you take a projection, not enough, because of course, as you change direction of sight, you might see other apparent crossings, etc. So the exact value is provided by the average over all possible directions. This is a geometric quantity. The other quantity that is geometric is the twist of the ribbon. And the twist of the ribbon has an expression that we can inherit it from Love book on elasticity, 1 over 2 pi. And we have a u, normal unit vector to the center line, cross, if you like, du ds along the arc length, and then you use the dot product with the tangent t on the curve ds. And this is, you see, it looks like that it depends on c only. So you would be tempted to think of this as a line integral, because it looks like this. It looks like a line integral. The point is that you need to specify the u, and the u is the width, if you like, of the ribbon. So in actual fact, this depends on the ribbon. And you can work out this quantity explicitly, a little exercise for you to do maybe this evening instead of going for swimming. And the idea would be, okay, you take u. You remember, if I have a curve in space, you take a cross-section, and in this cross-section, this is the tangent, you decompose in the plane, so to speak, in the cross-sectional plane, this u, any unit vector, in terms of the unit normal and unit binormal. Here, taking care of an angle, etc., etc. You do your computation, you derive with respect to S, so you use Frenet-Serre, and the result of this is that you can show that this quantity is equal to 1 over 2 pi, the total torsion of the curve, which is indeed a line integral, plus a contribution from a so-called intrinsic twist. And, well, let's say the full rotation of u of the unit vector as we go all around the curve. So this is just given by this expression, and I sometimes refer to these two quantities as total torsion plus this n, this intrinsic twist. In order to understand the writhe, I like to show you a physical model for that. This second term here. Yes, perfect. Here's my ribbon, right? It's very hard to buy a black and white, so I had to work on it in order to emphasize the two regions. Now, suppose you don't want to deal with torsion, okay? So you have a straight center line. And then you want to emphasize what this is the contribution, and this is your contribution. Is the rotation of the capital U around the center line of this supposed to be totally tight. Now, how this formula works, it's important to understand it, so allow me to do the following, because for some reason I prefer not to close the curve like this, but to close the curve or the ribbon like this. I inserted a twist. Don't worry, I'm not making tricks. I'm just emphasizing two things for you. And, okay, you see, imagine, first of all, allow me to think of this ribbon as a very, very thin, of a little width. Otherwise, increasing the width, things are not quite the same. And you put it on a plane. Imagine that you look at the normal to this plane, like so. You go around, and I force this ribbon not to have any twist here, and all the twist confined here. So I would say, okay, I compute this thing. This is almost planar, and for some reason I can compute the writhe, and the writhe is 0. I'll show you what I mean in a moment. And what I have is the twist, but also the torsion is 0, because it's planar circle, if you like, the center line. And I put in evidence this quantity, the intrinsic twist of u. And now, without opening my system, I just continuously deform the system so that I can get rid of the twist, and all the twist goes into the writhe. And this is the situation. You see that the ribbon is almost always perpendicular to the plane, so that means that the twist is 0. There is, of course, a little fluctuation, and this fluctuation can be controlled by the width of the ribbon. And this is the writhe. So measuring writhe, measure basically the amount of coiling that there is in the ribbon. Okay? Pay attention, if you think of geometric terms, the writhe is not bending. Bending is the integral of curvature along the arc length, whereas in here, hidden there is always a little bit of torsion. And by the way, a fantastic exercise for you would be to be able to extract torsion from there. Very hard. Nobody knows how to do it. Everybody knows that there is writhe, there is torsion, but nobody has succeeded to extract, to distinguish, if you like, contribution from curvature from contribution to torsion. Now, remember, just quickly, that the writhe of any planar curve, almost by definition, if you like, is zero. So all curves that have that lie in a plane have a zero writhe. Now, because of this, I don't have much time to tell you about this, maybe in passing by, but you can compute also this. You're saying, well, Renzo, but you have to take infinitely many direction of sights to have a true writhe because of this definition. No. In practice, it works very well. If you take, for example, 3 different projections along x, y, and z of the same structure, and you approximate the exact value very, very well. So imagine that instead of the exact writhe, I introduce an estimated writhe by taking these measures, projecting the curve or seeing the curve through 3 mutually orthogonal projections. And this was discovered in practice in biology. They take the DNA, they look at 3 or 2, even 2, of course, ideally infinitely many, and as you approximate 2, you do an error, but this error is basically very little, almost indistinguishable between the exact formula and the estimated formula. All right, now we are ready. For the moment, of course, there is much more to say, but this is basically it. This formula, Calogeriano is 1961, and White is, I forget, probably 1968, something like this, or 69. All right, can we now relate all this to helicity? Because you remember I already said that according to Whitehead, it was known a vector field times its cross, if you like, using vector field language, was known to be an isotopy invariant of the curve. So I think we can simply refer to the work that initiated by Moffat to establish a correspondence between helicity and linking numbers. So we have the following result. I just quote the result, and then I try to give you a hint on how to prove it. It's one part of the work is relatively easy. You can do it in a half-hour lecture. The other one is long and technical and is not so easy. Anyway, let me first come up with this. So imagine, for simplicity, imagine that this knot is linked with another filament, and now I think of these as vortex filaments. Now, linkage does not depend on the tubular neighborhood, on the width of this tube, etc., because I just look at the linkage between the center line of the green tube and the center line of the white tube. So that doesn't really involve any particular difficult thing. We know that helicity is an invariant of Euler's equation, and here we go. We have a following result. This is due to Moffat, 1969, and then the other part is Moffat and myself, and this is 1992. The statement is the following: the helicity, you can think of kinetic helicity of a vortex link of a vortex link. By link, I mean something like this as well. You know, this one of the components or all the components may be knotted. L is given by the following expression. So we have helicity. Remember, helicity of, say, this link. I emphasize that this is in terms of vorticity u dot omega dv, okay? And this can be expressed as sum over gamma I, gamma j, if we have I different from j components, gammas being the circulations of each component in the link times the linking number ij plus sum I equal j of gamma I squared SLI. Of course, you know Gauss linking number. You now know about this limiting form for a knot. So this part takes care of the knotted contribution from each of these components, and this takes into consideration the linkage. Yeah? Yes? Because you assume field lines to be localized in tubes, first of all. These tubes are... Sorry? So it's the volume of the tubes? Absolutely. Okay. Because otherwise it would be zero. Is where omega is defined. And then you assume also, to be correct, that these tubes have a small cross-section. It's not necessary, but they have to be vortex surfaces, the bounding of these tubes, plus small cross-section, so that you can come up with, you can take omega in the cross-section and to get it out in order to get the strength of these vortex tubes. The strength is not necessarily, it depends, if you like, on the size of, well, the strength is circulation and any size, but I take it as a suggestion. Important thing is that this result holds true for localized fields. That is important, and then it can be extended. By the way, why not? I can mention there is an extension of Arnold, I can't remember the year, 1974 perhaps, where he extends the same statement to field lines. Of course, it has to deal, you cannot really talk about knots and links, because if you think of field lines filling a volume, then you introduce an asymptotic form of linking number, and then you also assume that these field lines are kind of closing on themselves in this volume. And so if you introduce the concept of asymptotic linking number, you can still prove that this quantity is related to this asymptotic linking number of a volume filled by vortex lines, and is a topological quantity. So there is this earlier work of Arnold. Proof of this result is, well, I didn't say it, but evidently LK is the Gauss linking number, SL is the Calogero-White linking number. Proof, I just give you, hints of how to construct the proof. And, there is the linking part, let me call it, let me call it H mutual. And this is the H self, something like this. And so for the H mutual is the work of Keith, 1969, famous paper in JFM, where basically you remember that we introduced the linking number emerging from the linkage between a physical field line and an abstract line. And now this abstract line, I said a couple of times, you may think of a velocity line. So it's the linkage between the vorticity and this velocity line in that case. In that case, we had only one gamma because it was one line. But in this case, this second line that in their situation represented say, a velocity line. In this case, it's a vortex tube. So we have a contribution of two different vortex tubes through gamma 1 and gamma 2. So this is the mutual part of helicity. And what you do in order to prove this is that omega lines are localized in these tubes. And the U typically is derived from or given by Savoir. Okay, so by doing this, you work things out, and you can prove that this is you derive Gauss linking number. And when you do this, evidently you have your result that the mutual contribution to helicity is given, as I said, by this I different from J of gamma J linking number between I and J. All right, that was it. And then what about the H self? Well, H self is a pain because, first of all, a good idea is we want, this is where it gets really interesting. We want these tubes to have a structure inside. So imagine that you have a bundle of field lines, but not just a trivial bundle, so to speak. So a bundle, say, of circles on this planar circle tube. You want field lines that make, some complexity inside the tube, so that if you use your U unit vector to detect one of them, you want that this U rotates around even in the case of a planar tube. And even worse, if it gets distorted in space, you have contribution from torsion, etc. So that's why this is really hard to do. And so we have to think of decomposing the vorticity into a contribution of an axial, so to speak, axial field, and contribution omega m as a contribution from meridional field, or meridian field. Then you immediately have to demonstrate certain things. For example, that um associated to omega m is in dV is 0. This is easy. Second part is the Rife contribution, i.e. that UA dot omega m in dV is giving you the gamma squared. Remember, in this case, self. You don't have any linkage with anything else. You focus on the trefoil knot, say, any single structure, and then you have the Rife coming out. And then the third contribution is as made by two terms, so they are symmetric. UA dot omega m UA omega A, sorry. This one, UA omega m in the volume, this is just giving you gamma squared times, first you have to extract the torsion, and then you get to integrate something that involves inflection points, and amazingly, by Taylor expanding a curve with an inflection point, you find a torsion which is singular there because the Freinet is not well defined, but the type of singularity is integrable. And so you contribute with this constant of integration, and you can show that is indeed your n, the intrinsic twist, so that this is finally gamma squared times the twist. Okay, so this is so this is due to Moffat 69, and this is due to Moffat and myself 92. All right, so we are now at the position where helicity, to some extent, is done. You have information about its conservation, conditions under which it's conserved, and a way to calculate these quantities. Remember that the quantity Gauss linking number can be computed from any projection. You just count the apparent crossings, and because it's a topological quantity, it does not depend on projections. So the one you like is okay. Here you have a bit more of a problems because, the rise can be estimated by that. The total torsion, yes, you can evaluate total torsion. Let me say that total torsion doesn't count much towards the final result because you can, of course, it's just purely speculation, but you can think of torsion, even total torsion, except the particular configurations. Total torsion is just the amount of gradients of curvature, gradients of gradients. So it's unlikely to count much. We can estimate that 2-3% of the exact value. And intrinsic twist. Now, intrinsic twist, i.e. the twisting of these field lines in the tubes, is really what you want. Is very important because vortex filaments interact, reconnect, topology changes, and a lot of energy goes also in this interaction and exchange of twist from one structure to another through different scales, by the way. So one way to do this is, okay, this is hard to compute, so what I do, I say, okay, I can either compute this or estimating this from different techniques, but I know that counts only 3%. This is almost exact from 2 or 3 viewpoint or projection, and this is exact. So if you have access to computational methods or information from experimental work, you can work out this, and then from this you take away the linking number that you evaluate and everything here except twist, internal intrinsic twist. So you have intrinsic twist as the difference between this and these two. If you do not have access to computational measure or experimental measures, for example, in astrophysics, in solar physics, this is not that bad. Remember, it's A dot B, so through magnetograms you can get information about this, and of course it's a volume integral, that's the problem, but they can do it, and the linking number by just imaging contrast software, you can evaluate that. The structures in that case would be magnetic. I cannot say magnetic tubes because there is an astrophysicist here. I would say plasma loops. Remember, you do not see vortex tubes, vortex filaments. You see the dust that goes around the low pressure field. Similarly for magnetic fields, loosely speaking. You see ions, charged particles that by Larmor radius, background of physics, curl around the so-called magnetic lines, okay? All right, so we have everything. One last thing about the helicity and linking number I want to say, because I started talking about multivalued potential and all that, and you may wonder why on earth I started from there. There are two good reasons, and today I give you one reason and tomorrow the other reason. And one reason that I give you today is work done very recently, and is basically formally reproducing Kelvin's work. So that's why I find it amazing. Now, I have to give you some sense of why on earth I want to tell you about this, or maybe I introduce the result, and then I want to give you an applied viewpoint of this result. So the problem is, if you care about, in particular, magnetic fields, but vortex filaments as well, if you think of a tokamak, okay, tokamak is a toroidal machine where inside there are magnetic fields, and Of course, I'm sure you know what I'm talking about. In France, in particular, near Grenoble, there is a huge center that's been built for the next torus experiment. Well, this is definitely a multiply connected domain, and if you want to compute the helicity there, then you have a problem, because I use vortex dynamics symbology now, but it's the same thing for magnetic field. U dot omega in dV is not good enough, because in multiply connected domains you have to define a gauge invariant quantity, and this is not gauge invariant in multiply connected domain. So how to adjust the problem? I won't go into details. I just show you the result, because this is due to McTaggart and a topologist, and Valley. A collaboration that led to this result. I don't have a date. I'm terribly sorry, but you will get the date in the notes. It can be 2000. Let me strike a balance. 2012, maybe 13. I'm not sure. Anyway, this result is that a gauge invariant helicity in multiply connected domain, so helicity in multiply connected domain, this helicity, to make it gauge invariant, you have to use the information on the number of holes. You may remember the Kelvin's formula has a sum there, and then there is a kj. I'm happy to call it circulatory constant, as using the language of Kelvin, and then we have a omega dsj through sigma j. If we have one hole like this, you remember we cut the surface with a Riemann's cut, and one integration along a line integral along this curve. We may call it a cycle 1. I mentioned the role of cycles when I talked about Kelvin's result. So you may interpret this as the integral of a line integral of on cycles, and this, you can convert this, but let's leave it like this. This is the flux, if you like, of vorticity through a Riemann's cut, which of course can be reduced to a line integral as well, and the other cycle would be something like this, gamma 1 prime. These cycles are the generators of the homology, let's say, of the system. So if you have, for example, a double holed torus, a two torus, then something like this. Then, of course, you will have one generator, gamma 1, and the other generator, gamma 2, and eventually you have to cut to get this domain simply connected by inserting two surfaces, two sigmas there. Now, what's the relevance of this in applications? Well, of course, I mentioned also tokamaks, but I want to be a little bit more precise. It's to do with periodicity or multiple periodicity, in other words, holes, in numerical simulation. When we hear the presentation of results done in a periodic box, the periodic box has multiple periodicity, maybe two sides, or maybe the three sides of the box, because one side is equivalent to the other. And so you have to correct helicity computation according to that. Yes? No? No, we can do it. Yeah, sure. Okay. Yeah. Not necessarily cut from the extra one to the or. No, absolutely. You can find your cut surface as long as you get the simply connectedness. Yes, yes, yes. All right, so I'm sorry I just was a bit late with all this material on helicity and linking numbers. I wanted just to remind you the basic information on linkage. And remember also, because we want to leave some curiosity for the last lecture, remember also the example of the Borromean rings or the Whitehead link, because these examples show you that there are very simple linkage with linking number 0. So if it is linking number 0, the helicity is 0 if there are no knots there. Okay, so we are not yet happy, as it wasn't Maxwell when in his book he reproduced the case of a Whitehead link ante litteram. Right, so I would like to tell you now, today will be really an excursus of concepts and not much, I'm not going to prove stuff because I want to be rather quick in showing you what is known, but you will have references, etc., to help you out with the proofs. So I mentioned this problem related to Biot-Savart, desingularization, and then eventually, I mentioned vortex knots, because I want to tell you something about vortex knots as well. Okay, so the problem, as usual, very well known since time of Kelvin, is that we have a 4 pi and then the integral on the volume. I can reduce everything to a line integral if you like, for simplicity. X minus x star, that's why I took out the gamma. And then this is just the cross product with dx star. Remember, in this case, x star is where vorticity is placed. And dealing with this, it's okay as long as we stay away from x star. Now here I just, for simplicity, I just show you the line integral. But if you think of a tube, then of course you have a volume integral. I'm assuming that the cross-section is small, and again the vorticity through the cross-section gives me the strength of the vortex. But nevertheless, this integral is awkward. You know, I want this x is the induced point somewhere here. And then I have an x star here, or an x star on the center line, or an x star in the tube, any place you like. And then I want to find out the induction, self-induction of the velocity at this point, as these points get on the tube. Why? Because as closer I am to the source field, then the better it is. I have a more accurate information of the induced velocity. And what people say simply is, okay, the velocity induced by the vortex is, and what they mean is the velocity at this point. Of course, it's not true. This is what we like to think, is a velocity very, very close to this point. So before going to desingularize this integral, because evidently you see the singularity is there, well, we can have a simpler approach. And the simpler approach is, okay, well, I cannot go here or anywhere inside because there is a coincidence between x star and x, but at least I can go here. On the boundary, already dangerous, near the boundary, near, as close as possible to the boundary. So there are limits, right? There are limits involved because I cannot go to the boundary. I have to take a limit as some distance goes to 0. Now, this has been a problem for several years. I like to tell you because I spent so much time on this when I was, believe me, your age. I wasn't in any doctorate. I was 18. At the age of 18, I asked for, they asked me what I wanted as a gift for 18 years old, and I asked the real book by Lamb, So I encourage you to read it. It's a thick book produced in, I can't remember now. Anyway, that was a good exercise to understand many, many things. Hard exercise. Anyway, what I wanted to say is first, I do some simple remarks here. And the first remark is we heard about LIA. I will talk about LIA today as well. And LIA, I don't think anybody knows really, or I mean, I wrote it, but doesn't matter, is the origin of LIA is in Levi-Civita's interest. Levi-Civita was supervising the thesis work of Darius in Padua. And already in 1890, he was curious about the gravitational potential of the Saturnian rings. And in order to understand the gravitational potential on Saturnian rings, he assumed that these rings were really like thin tubes. And on thin tubes, he wanted to develop an asymptotic theory. And so you have, at a certain point, one line representing a center line when you are very, very close. And it's very interesting that he noticed that a point external to this line, imagine that this line is made of X star point, the source point of the gravitational potential, so masses. And he wanted to investigate how the induction was going as this point X was approaching any of these point X star. And then he discovered that there is a problem if this point X approaches this segment for the moment in this fashion. So he excluded a little angle, and from there he developed his theory. So when the thesis was given to Darius, he already had an extension of this theory to curved parts of these rings, etc., etc. Amazingly, that I contributed to find again the work of Darius. Amazing, why? Well, we had the 2 world wars, but in 1933, Darius was already doing something else, and Levi-Civita was invited to Paris at the École Polytechnique by Villa to give a series of lectures. And amazingly, he decided to talk about Darius' work and his own work. Not one lecture, several lectures, so that Villa collected the contributions, and we have the contribution from Levi-Civita in the 30s. But all this went lost again, so I found myself in Cambridge, in the MTP, in front of Bachelor, and I told the story almost when I arrived. So as a grad student, I went to Moffat, and then I went to Bachelor, and I told them that all this was known at the time of Darius and Levi-Civita. And in front of me, taking tea, was sitting Bachelor. Now, Bachelor took that all this approach that I'm going to tell you in a moment very, very quickly is in his book. His first edition, 1967. And he thought that was a real contribution. So he was astonished. And the ethics of certain people is that he said, well, Renzo, if all this is true, you have to absolutely write everything in English, and I will do all I can to have an important paper published. So I published this note in Nature, and that had a huge success. I've been asked 400 plus printed copies of this paper. At the time, PDFs were not available. I was already in California. Anyway, so what is... So the point of desingularizing this, my best reference, why not? I'm perfectly happy to address you, Bachelor's book. It's called Introduction to Fluid Dynamics, and is a very well-known book. And you can go to any edition. Probably there is an nth edition of 2000, has been published many, many times. And in this book, you go to chapter 7. So chapter 7 is on vortex filament dynamics, chapter 7. And you see the derivation that I sketch in just a few moments because I want to talk about something else. So you go like this. This distance is rho. Rho is basically x minus x star. And mind you, the derivation doesn't make functional analysts so happy because it's kind of crude. And I'm still waiting for a better proof, but of course there are papers around. Right, so dx, we have to construct this integrand, and dx star is approximately, and here we go with one first approximation. This is coming from Taylor expansion. T, unit tangent, C, N, C is curvature, N, S, possibly, maybe, if it is not wrong. This is dx, so this is ds. And then some others. So you start building up your stuff, x minus x star. And then I give you just an idea that x minus x star taking the mod is given by, well, you can check, okay? There is an x2 squared plus x3 squared plus 1 minus x2 times the curvature, and then this is s squared. I told you, you use Taylor expansion. 1/4 c squared s to the 4th, and then all these, remember, x minus x star has to go to down here, so you have evidently a cube here. And now these x2, x3 are just, you take a plane here and you start decomposing everything along x and y, x2 and x3, taking this as an x1, okay? These are the components of the vector x at a point, or near a point, otherwise they would be an x star. And then you do all your calculations, and you come up with something that I omit the technicalities. There are two limits to take when you do the integral, and there been a great discussion many years ago on how these limits should be handled, and etc., etc. And you get you are at x. Now, remember, we want to have the first order contribution because this vortex filament, this vortex tube can be huge, far away. But because the velocity, as you know, or better say, because of the green function, there is a 3 here, the integral has to be done, so you ask for convergence. And if you ask for convergence, you just neglect long-distance effects that do matter, but do not contribute to the eventual emerging singularity that you have as you get so close. And when you do this, you find, allow me to put an equal sign, although I meant an approximation, gamma over 2 pi rho e theta plus gamma over 4 pi capital R logarithm of L over rho. This is along the binormal direction, plus I say a quantity u, I should say maybe v, changing, well, okay, I say u finite. And now I tell you what I mean. So you have rho is the distance in, say, cylindrical polar coordinates. So you imagine that if vorticity is directed in this fashion, you have the fluid that rotates like this. And it rotates like this if the vortex tube were straight. We heard from the lecture of Luis Vega that we have gamma over 2 pi rho e theta. That's it, because it would be straight. So we have only azimuthal flow around the tube, and the tube, a straight tube, would not move. Okay, and there is a singularity, 1 over rho. 1 over rho. So this is one problem. Then we have this other contribution very close to the vortex tube, gamma over 4 pi r. What is this r? Well, this r is what you know very well. The r is this radius of curvature. So I can rewrite this as gamma over 4 pi c curvature. And then there is a log of L over rho. And here we have another discussion. What is L? L is a distance along the center line that is not so well defined. Okay, so because I like to have some expression that is a bit more precise, instead of L, I take alpha r, the contribution from an arc of a local circle. So I will have another big R here because alpha parts goes into U finite. And then I have R divided by rho. R divided by rho, I do something else now that is terribly unpleasant. I want to go on the boundary. And on the boundary here, I replace rho with sigma. This point is on the boundary. I know what you think, because I do think the same. We have lots of problems there. Okay, a little bit away from the boundary, as close as possible. So if it is a sigma, the radius of the cross-section, assuming that it's circular, which is also wrong, is not a solution of Euler's equation. But if it is very thin, you can assume that. Then you can have your sigma here and your sigma here. Okay? So I can put this and I can put this. All right, I stop here because I'm ready to go to two different aspects. One is of course, the vortex ring formula that has not been mentioned at all, amazingly. And the other one is LIA. And then I just tell you something about this desingularization. Capital R. Oh, capital R is the radius of curvature, of this tube computed here. Right? So it's the imagine the vortex ring is the large R of the vortex ring, and the sigma is the small r of the torus. All right, so I have, before leaving, I'm not leaving this, but before leaving part of this, I want to tell you something, because it's in my mind since I was 19, and I never kind of succeeded. And I asked so many bright people. So it's not easy. It's in between history and vortex dynamics, because some of you came to tell me that we're interested in these aspects as well. So let me conclude that Kelvin gives the formula for the propagation of a vortex ring, U, along the axis. We heard that. And this is gamma over 4 pi r, you take it from there, and then there is a logarithm of 8r over sigma minus 1/4. And is along the binormal, okay? So question to you, bright students. The question is, please derive this formula with the knowledge of 1867. Has to be done one page. One page. I don't want to hear about elliptic functions and all that thing. I don't want to hear that. I want to find this formula. It took 1 hour, and we don't know how. And when Tate published his book, his translation of Helmholtz's paper, the evening before, he added a half-a-page note saying, well, Helmholtz has done so much, but he didn't give the velocity formula for a vortex ring. And it's so important, and he gave this formula. So I encourage you to do whatever you want and come up with the result. It would be great. I tell you, it would be fantastic. But please, that's the effort. You have to investigate a little bit the knowledge of the time. Don't come up with elliptic functions. Good point. Profile. profile. We have several profiles of vorticity. And for Kelvin, very easy. Delta Heaviside distribution. Uniform profile, you take vorticity equal to 1. And you get 1/4. If you like to take vorticity only on the boundary, a very strange problem, in other words, a hollow vortex, then you have, this is 1/4, then you have 1. And then there are other profiles that gives you a half. This is all the work done by Kelvin, Higgs, and so many others. And J.J. Thomson get 1, making a mistake. He got the Adams Prize from Cambridge University, one of the top prizes still given around. Okay, with an amazing piece of work, by the way. But he makes a mistake, so the one that J.J. Thomson, he was asked to clarify this fourth. And in clarifying the fourth, he got 1, so he got some credit. Kelvin was wrong, but then Kelvin was right, and Higgs came and showed that J.J. Thomson was wrong. By the way, we're talking about the man who dropped mathematics. He was 24, he got the Adams Prize, and then in 1906, he discovered the electron, so he got the Nobel Prize in physics. So, okay, let's stop a few minutes, please, and then we resume. Can I start? Yeah. So I'd like, I'm very happy to just quote this result that is a work of many years by the group, actually was mentioned yesterday, the group at the time in Bath, and so Professor Frankel, and also Mel Berger in Boston. So indeed, as was mentioned yesterday for the leapfrogging, we can quote this theorem, which puts at rest almost 70 years of discussion. So this is Frankel and Berger, and is 1970. So I want to state it in full because, after all, it's a school on vortex dynamics. It makes sense. There exists a two-dimensional region. Maybe some of the wording is mine. Apologies for that. Let me call it omega 2 closed. And this is indeed the sum of omega 2 and the boundary of omega 2. For some reason, there is a 2. With vorticity, omega equal 0. I'll tell you why there are no vectors here. We are in a plane, etc., etc. And this is in R2 mod omega 2 bar. So in the complement region, flow field velocity, the velocity of the ring, u, and vorticity omega, defined in omega 2, so to have a streamline, we have to have this matching condition. Streamline psi equal constant on the boundary d omega 2. The 2, now I realize by writing, has to do with the fact that we are in 2D. And psi equal 0 at infinity. It means velocity is at rest. Infinity. Okay, the propagation velocity u of the vortex is given by formula u equal gamma over 4 pi r logarithm of 8 r over sigma plus f of omega plus the correction term, so this is contribution, and the correction terms is of the order of gamma sigma to the 4th divided by r to the 5th log 8 r over sigma. And knowing the literature, I bet that somebody came maybe 2 years later, 3 years later, 4 years later, improving maybe this order of accuracy. I don't know. Where sigma, you know, and r, capital R, denote the smallest and the largest radii of the torus. I told you, is about a vortex ring. I should have done a picture before. And f of omega denotes the vorticity. The vorticity distribution on the cross-section. So, okay, sorry, I had to say it earlier, but anyway, this is your vortex ring. Is not thin at all, so but not too much. Okay, something like this, and it has a cross-section here that is not circular, has to satisfy the Euler's condition for psi equal constant, and it propagates according to the circulation around it like this. So R is this, and sigma is this. Okay, so I'm sorry, it's a bad drawing, but it gives you the idea. So this is so this f of omega, remember, before in Kelvin we had minus a fourth, then 1, etc. So these changes are due to the fact that it depends on the vorticity distribution on the cross-section. So if we have, say, the cross-section like this, then we heard yesterday that the vorticity can have a profile, say Gaussian profile or other profiles, and according to the profile you get a slightly different contribution to the velocity of the vortex ring. Right, so I just wanted to mention this because it's important for a number of reasons, and of course is a steady solution to the Euler equations. Remember that if you were looking at the cross-section of this profile, now of this torus, how to draw this? I will put let me think. Okay, so this is, it would be, you look at the cross-section and remember that what you would see is something like this, and these are the streamlines, okay, and equally this, of course. So these are called the D shape of the streamline pattern, and imagine that this is a torus. So it's not at all of a cross section. The cross section is a D shape, and the streamlines are packed on the center. All right. So if you think of a vortex like a helix, then you have to think of this perturbation of the circle, so to speak, that rotates with the torsion. So it's not an easy problem to work on. And what they did, because of symmetry, etc., they went to the cross-section. And so these suppose that this is the external boundary. That would be the omega 2. That's why. Okay, so they are. And the velocity, you are co-moving with the vortex, so the velocity is basically u here, right? So this is the formula, and all right, so that's only mentioning this result because, of course, it puts at rest a lot of discussion about this F. And of course, in viscous flows, this F contains information on viscosity. And the viscosity, of course, changes the profile. Because that is the steady solution to Euler equation. If you take a circular cross-section, you may say, as we heard, you assume very thin vortex. Okay, if I go for a thin core vortex compared to the radius, etc., then I can say, okay, I just take this. And the psi, the streamlines around it, but is wrong. Is the best you can do, you may say. Yeah, of course. Kelvin surely did that. Surely. He assumed a thin circular cross-section. So my advice is to go to Wikipedia and look for the steady solution in MHD, magnetohydrodynamics, because it's exactly the same problem. And you look for tokamaks, and you look at the cross-section of tokamaks, that is the shape. So the steady solution to Euler equation is exactly the same as the steady solution for MHD in a torus. There are many of them, correct. And so in that case, the main solution is referred to Grad-Schaffernov problem, but this is... Okay, so this is just to have some information, nothing else. But this paper, or at least the series of papers that leads to these results, are beautiful but hard. But I encourage you to have a look. There is they consider the vortex, the straight tube, and then they deform it with curvature, and they do an asymptotic a mapping, etc. Okay, right. So we have a formula for the vortex ring, but I'm very happy to say, okay, we neglect this change from the cross-section circular to a D shape. We rely on the fact that the cross-section is basically circular, assuming that we deal with very thin vortex rings. Now, if we do that, fine, we can think of taking the argument of the logarithm, which is r over sigma. Of course, it's large because we go to sigma very small. And I cannot say, and indeed they would be terribly wrong to tell you that I assume r over sigma constant, but I take r over sigma very large. We are in the flat part of the logarithm, and now you do another kind of approximation. You assume that basically in time this ratio will not change. So if the ratio does not change and you are on the flat part of the logarithm, so to speak, then you can neglect all this, and 8 over r becomes r over sigma, very large. So we are now case of very, very thin vortex rings. Exercise. Just give numbers. Put numbers there. Put numbers. For example, I don't know. You saw the movie by William Irvine, and the vortex, or at least the the vortex has been visualized by these little bubbles. Imagine that is, I'm just making up numbers because the real numbers are in the paper and I don't remember them. But suppose, just for simplicity, imagine that this vortex is 1, 2, 3 centimeters, and then is maybe 1 meter long. Try to put this number there, and you will see that is not good enough at all. At all. So when Professor Vega asked William Irvine about LIA, of course, He was the wrong person. He was the wrong person to ask, because William Irvine, I know him very well, he probably said, no, LIA is not good enough. You had to ask somebody doing superfluid in helium. That is the context. The context is the right one, because the vortices in superfluid helium are of the order of, say, centimeters, 10 centimeters. But the cross-section, sigma, is of the order of the Armstrong, 10 minus 10. Then this quantity is really basically constant in time. And there is where you are happy to use LIA. That is the only context where LIA makes sense physically, I mean. Then, of course, the beauty of mathematics is undisputable. So, you know, I have a gamma over 4 pi. So it's a constant in Euler equation. I can rescale gamma over 4 pi, and I get, remember we had 1 over r, so I have a c, and then my binormal. And this is the velocity induced by a thin core vortex ring. So this is fine. So I did, when I started my PhD, more or less, because I followed up the work of Darius, etc., I did some work on that. And of course, you heard so many important aspects about this. It's a beautiful equation related to nonlinear Schrödinger equation, Heisenberg continuous spin chain. And because it's related to NLS, you have infinitely many invariants, soliton quantities. I'm going to tell you something about these soliton quantities, maybe later on today or early tomorrow. I don't want to talk about those at the moment, and there is a reason for that, which you will guess in a moment. Under LIA, we have, first of all, is a binormal flow, so definitely the length of the filament does not change, is preserved. Total length preserved, and that makes Professor Pumir very unhappy, because we have stretching. Remember, stretching is a key to turbulence and other aspects. So LIA is maybe nice, but physically speaking, doesn't help vortices in fluids, in real fluids, say normal fluids for us, for the universe, fine, because the superfluid helium is present in large majority. And another quantity that is conserved, I told you there are infinitely many, but at least one that I want to tell you immediately is total torsion is conserved. You remember the role of total torsion, E2I total torsion in the Asimov. And then we have two other remarkably, in LIA as well as Euler, we have a linear momentum and angular momentum conserved. They didn't want me to speak more on this call, so I'm joking, and I don't have time to tell you, but there is I quote a paper of mine now 20 years ago, where I showed that linear momentum and angular momentum under LIA allow to interpret these quantities as projected area, so you can compute through computation of projected area, i.e. areas of subregions of a graph, these dynamical quantities. And I'm pleased to tell you that some physicists just put at work these ideas. Okay, I want to tell you something about LIA in terms of solutions in space. And one work that I did is back to 1992, at least that was the publication. And so it's a, long time ago, 30 years ago. And so the theme is LIA vortex, torus knot solutions. I might be late with the actual aspects of desingularization of Biot-Savart. I'll start tomorrow maybe with that afresh. So, but don't worry, the last lecture will be with some movies, okay? So movies will be the attractors of our last lecture. Now, torus knot solutions, we have, I'm terribly sorry because I missed this information in my notes, so I'm not able to replicate this to you right now, but an important, the first important work comes from Kida. Kida, 1984, produces, has a paper in Journal of Fluid Mechanics where he derives torus knot solutions to LIA in terms of complete elliptic integrals. And this is not, is almost, okay, so it's a beautiful, beautiful work. So what I mean by torus knots, well, okay, torus knots are a particular class of knots. So for example, our trefoil knot, something like this. And, you know, on a torus, if I look at the mathematical torus from top, I learned from when I was your age how to draw these things in order to construct a knot of any complexity. And this is so simple and beautiful. I reproduce it here for you. Imagine that this line in green is the vortex line. I do like this, then like this, then like this, then like this, and then like this. So you are seeing from top a trefoil knot, okay? So this knot, I call this knot or K, doesn't matter, Q3, is going 2 times in this direction, in the longitudinal direction, and 3 times in the meridian direction. So it embraces the small radius of the torus 3 times. And there is a way to prove in topology that knots of type TPQ that stays on a torus are topologically equivalent to knot TQP. The TQP knot, remember, so in this case would go 3 times in this direction and 2 times in this direction. So this is a purely topological statement, but dynamically, do we have an equivalence? And if not, why? So I learned my knot theory when I was in Cambridge by a great man in knot theory. I was in the other department, you know, I was going across the Bourbachian cut, and Licorice, Ray Licorice. But I came back, going through, I came back with the idea, so if they are equivalent, energetically are equivalent, dynamically are equivalent. So I put myself this question to Moffat, and he told me, as usual, he said, Renzo, this is good for you, just work on it. So, okay, I did a little work, and I start with LIA. So excuse me if it is so simple. It is so simple, has been attacked with other techniques, very sophisticated techniques. For example, one work that comes to mind is Annalisa Calini in US. But allow me to tell you what I did when I was so young. So it's kind of simple. In order to study this problem, I want to refer to this velocity LIA. We heard many times, so just the dot refers to the fact that I take the time derivative of the vector position x, and the prime, I use the wedge symbol, otherwise it's a cross product with the tangent and the curvature along the normal. So we have curvature times binormal written like this, okay? Imagine Cartesian coordinates. And the beauty of the intrinsic description goes totally to the bin, because when you rewrite LIA in Cartesian coordinate is a mess, but it's a good exercise. So I just give you a reference. This is more or less 93 maybe. So I want to give you, first you go like, okay, maybe something like this. Let me do this. I will avoid this stage. This is Cartesian coordinates. And then you get to cylindrical coordinates. So LIA in cylindrical coordinates get to this mess. Cylindrical coordinates are alpha and z. Okay, obviously you have your vortex ring, very thin, and you center this ring on the z-axis, and then, as usual, you take the ER direction. So R is the coordinates, and then this is E alpha, if you like. Okay, this would be easy. Okay, so in this is just to show you how life. Yeah. You're right. I realized when I was drawing this. So the problem is, okay, given the fact that we know that the vortex ring is a steady solution to Euler equation, I go to very thin ring, so I rely on LIA. Okay, now I have LIA for a vortex ring, which is the one you see here. So it's a planar ring, and of a given radius. And then I want to, this is why I said that this is a very simple approach, has been refined by many authors, but I want to linearly perturb this quantity, this filament, this line, in order not only to perturb it in this direction, but also on this direction. So this is called the longitude, and this is the meridian on a torus. And if I perturb this line so that in meridian and longitudinal direction, I want to perturb it also in order to have a closed torus knot. So I have to take these numbers P and Q. I have to take them P and Q are co-primes. And of course greater than 1. If P and Q are 1, you get the circle. Not quite. You get a loop that is a kind of a distorted circle. If you take P and Q primes, for example 4 and 2 and 2 and 4, you get links, torus links. So the question was at the time to look for torus knots, because, remember, I don't want to boast anything, remember I was guided by the result of Kida. Kida has a theorem that says that these torus knots are solutions to LIA. Problem with Kida is that solutions were written in terms of complete elliptic integrals. And no matter how you play with them, there is no way to extract an analytical expression in closed form that you can use eventually. So this is the result. This is a very important result. And because I relied on this, I knew that if I was doing a linear perturbation of the circle, probably I was getting a sort of small amplitude perturbation from encapsulated in these elliptic solutions. And indeed, it was the case. So by doing this, this is straightforward. This is just algebra. So it's so easy. I'm not at all proud of what I did. It's just a kind of exercise, but it's tricky. Anyway, so this is R, and R, I just want to give you the idea, so I want to explicit this so that you see how messy it gets. This is R alpha prime. Remember, primes are arc length derivatives. Minus 2R prime, alpha prime, Z prime, minus R alpha double prime Z prime. And then I have a R alpha, oh sorry, this is R dot, because I have on one side the velocity, on the other the space contribution, the gradients. This is R alpha dot, and this is minus R prime Z double prime plus R double prime. I shouldn't spend so much time in doing this, but I just want to show you how it gets bad. This Z prime, and this is Z dot, and is 2 R prime squared alpha prime plus R prime alpha second minus R second alpha prime. Oh gosh, what I've done. Better to leave it. Alpha prime cubed. Yeah, right. So this is LIA in going through Cartesian coordinate in cylindrical polar coordinates. Right. What we can do with this? We can perturb it. We can perturb this. This is an exercise typical of what? Should I say maybe? Okay, I'm weak. First year PhD student. A bright student like you can do it in maybe high school, because it's not so, really, believe it, it's not a joke. It's simple. You take R, what I did, R, you take R given by the fundamental solution, R0, the circle, and you perturb it. This is what you learn, at least in Cambridge. Epsilon R, where R1, where this epsilon, I take epsilon very small, so this is the order of sigma over R0. You see, R0 is this R, and sigma is supposed to be the thickness of this filament. So you set your conditions like this. Alpha is S over R0 plus the perturbation, epsilon alpha 1, and then Z, you have to remember that the 0th order situation is the propagating ring. It propagates with time. So we have to put time there, and we have T over Z over R0. Why this choice? Oh, this choice is forced. You know, you have to choose this because plus epsilon Z1, because we heard many times the vortex ring, the smaller it gets, the faster it goes. So it's inversely proportional to R0. Now you do this, you take this. I'm not going to do it, no way. And you plug everything there. And then, as usual, you delete terms and you simplify stuff, and then you want soliton solutions, traveling wave solution. I don't want to use the word soliton here. And so you learn that you introduce a variable psi, which we heard also in the talks, S minus, I use a K, really, maybe. Okay, anyway, KT. Okay, so this is a traveling wave solution. When you do this, you couple the variables of space and time, and so everything gets easy. So you plug that into your equations. You do work because you have to insist on the fact that you require that this curve is periodic, and also that it wraps a mathematical torus a number of times p along this direction and q times along the other. Okay, so you have to work out on plug the right conditions in the middle here, and so you go to visit your supervisor maybe 3 times a day in the hope that he helps. Indeed, he helped. And so you get the solutions. I don't want to bore you with this, but I just like to write down the solutions, which do not look so nice, of course, but at least are in explicit analytical form. And the solutions are this. I want to write them down. TPQ, your torus knot, and this is made by R, by alpha, and by Z. And I remember linear perturbations. So we have R0, first order, zeroth order, if you like, plus epsilon sine of this psi, the traveling wave combination of S and T R0. And we have this parameter omega, W. I'm going to tell you about W, I should have done already. Then we have S over R0, this is zeroth order for alpha, plus epsilon 1 over W R0, cos of, as usual, psi divided by R0 W. And then the Z, zeroth order, T over R0 plus epsilon square root of W squared minus 1 divided by W squared cos psi over R0 W. Now this W, from Kidas there is no way to see what's going on. But here it's so clear. Well, of course, we have sines and cosines. That's obvious. It's typical of torus knots. But then we see the role of W. What is W? W is a winding number. Is the winding number is a topological invariant, almost trivial because of definition. Invariant, and is defined as a Q over P. So the number of wraps in the small along the small cross section divided by the number of wraps in the longitudinal direction. Now, better to stop here, but no, not entirely. I have still 2 minutes to go. I want to tell you something. Well, first of all, I'm not going into that, but because you have the solutions in this explicit form, you can investigate stability. Stability. You will see in the notes, because I don't have it. Maybe tomorrow I put a slide. Remember, we started from Kelvin's. Oh, Kelvin was a little bit devilish. At a certain point, to convince everybody that his theory was fantastic, he stated, talking about the trefoil knot and thinking of all possible knots, he stated, we may confidently judge that the knot is steady and stable. Whoa, what a remark. It would be a clay problem. I told many people, you know, Constantine and others, that this would be a great problem because remember, steady solutions we have not LIA, not LIA. Steady solution of Euler equation, we have only the vortex ring. Finite cross-section, blah, blah, blah. It would be amazing to prove this. But we may confidently judge. No. So, for example, with these solutions, I could investigate stability. Steadiness and stability is a linear perturbation of a steady solution. So to some extent, we can look at stability. And you can find something very interesting, also energetically. You find that the knots 2, 3, for example, the trefoil knot, it goes, let's say numerically. But you saw the trefoil knot produced by William Irvine. It goes steadily for some numerical time. It rotates, it moves, and it travels in this fluid without any change, remarkable change of shape. And I will convince you with some other numerical work that I've done very recently on vortex defects. We will talk about defects quickly in the last lecture. But the knot 3-2, the knot 3-2, as it starts, it opens up, it flowers out immediately. And it reconnects, of course, LIA breaks down, etc., etc. So we investigated this problem in a very clever, in a nice way. I don't want to attribute myself. So we took these solutions of LIA, and I asked somebody, Carlo Barenghi, who has a superfluid code in Newcastle, to run these equations under Biot Savoir. not under LIA. These are solutions to LIA. But what about Biot-Savart? Biot-Savart takes care of everything. And indeed, this was the result. These are, let's say, to some extent, confirming the stability result that I published earlier on, and these go immediately unstable. So the TPQ are P and QP less than Q. These are stable or linearly stable because, you know, stability is a big business. Linearly stable, and these are definitely unstable. Unstable. Right. This is a little remark. We will be back to torus knots, etc., in a little bit more sophisticated context. I want to end up today with this information. So we have LIA, we have solutions in the form of torus knots. Oh, wow, that's interesting. We have torus knots. We have at least a class. Symmetry is important, a class of knots that are quite simple, described by sines and cosines. Can we investigate other problems of this type? For example, we have knots and infinitely many conserved quantities, because remember, LIA is related to NLS. And we have this word, knots. What about knot polynomials? And 1 minute, can I go 1 minute? And so I'll be very quick. So another piece of work that I did when I was at that time, so is published, I don't know, 92, is to take, I can't remember because in my notes it's not here. Anyway, if you go to, so think of NLS and think of the work done on integrability on NLS and go for Sakharov and Shabbat. I met both of them at that time. 1972 was great because I visited, 92 I visited Moscow and I could talk to both of them, in particular Sakharov. And you realize that they, in that, at that time they had a paper. I won't do the formula for you because it's a bit elaborated, but we have a recursion relation that generates, so it's a generator, generates conserved quantities. And these quantities, and these were expressed at that time in terms of psi, the nonlinear Schrödinger wave function. But in terms of psi, remember, infinitely many. So my question was, what are these? You know, it's nice to say that we have infinitely many quantities. What the earth are doing there? Yeah, they are solid unconserved quantities. A nice way to phrase things, but still, why don't you admit you don't know? That's it. So what I did, I used the inverse Hashimoto transform. Hashimoto transform is a psi relating curvature and torsion. And now you use the inverse map, and by the inverse map, except at the point at the origin, where, of course, psi of whatever curvature is not defined, etc. But apart from a single point, all the rest works fine. So if you go to the inverse map, you find these quantities. So remember, we have total length that is conserved under LIA. LIA. This is LIA. And then I told you we have total torsion that is conserved. And then by keep going, you have the linear momentum, the angular momentum, infinitely many. So I can go on and on. So the other quantity, I'm sorry, I'm just making, is a curvature squared in ds. And then the other one is I put something like this, curvature squared times torsion in ds. So you can interpret all these quantities, not only, first of all, in terms of global geometric quantities, and also in physical terms. For example, well, this is total torsion, but this c squared, remember velocity is c along the binormal, so this is kinetic energy. This is almost helicity, is the writhe, because there is no internal structure, and so on and so forth. And then this one, I can't remember which is the Hamiltonian of the system, and so on. the Lagrangian, because the Hamiltonian, the Lagrangian of the system, and so on. So at least of the infinitely many, at least 5 or 6 are interesting. Now, I conclude with this. So, but what you notice is this is a length, scale like a length. This is 1 over a length, so it's a pure number. This is 1 over L, 1 over a length squared integrated over a length, and so on. So all these quantities scale down as L2 minus n. So I can construct a polynomial of this that is made by these quantities. So 1, 2, all these quantities are the integrals of the NLS. And all these quantities, I can scale up these quantities by multiplying, for example, this by a number, this by L length, this by L squared, so that I get pure numbers, and I get a polynomial. I have a polynomial and pure number and torus knots. So question is, can we, by using LIA, identify the polynomial of knots in terms of polynomial constructed by these conserved quantities? This was, I'm afraid, this is still an open problem and is considered extremely difficult, but nice, because it's related to the question I put this morning to Luis. There is a recursion operator that is a little bit nicer, in my view, than Zakharov and Shaba, and this is due to Langer and Perlin, beautiful paper number 1, issue 1 of Journal of Nonlinear Dynamics. Jerry Masden came with a manuscript to me and said, would you publish this paper? And it was beautiful. So you go to this paper, forgive me if I can't remember the year, but you will find the year. You have a recursion operator in terms of global geometric quantities. And so you have a way set to work out any connection with knot theory. Thank you very much for your attention.